Okay, so this lecture is going to focus on balancing redox reactions by way of half reaction method. We talked about this a little bit in class today. We did a kind of a brief overview, and in this lecture, we're going to look at two very specific examples. One, even though there are no acids present, it's considered, and well, we treat it just like we would a neutral equation or a reaction, but we're going to treat it just like an acidic solution, okay? So what we do is we balance each half reaction and then add them together, canceling out the electrons. Because the whole point is that electron gained must equal the electrons lost. So here are our generic rules. First, we have to assign oxidation numbers to everything to discern which element, which reactant is actually oxidized and which one is reduced. So we look at both the reactant and product side to see what happens. But once we know what's oxidized and what's reduced, then we can go ahead and separate them out. Remember, if it's oxidized, there's a loss of electrons, and the lost electrons are written on the product side. Remember, the plus sign on the product side, we're going to think of as and, not add together. The plus sign on the reactant side, we're going to think of as add together. So once we write oxidation states for each thing, and then we decide what's oxidized and what's reduced, we actually write the two half reactions. When we do that, we're first going to balance all elements that are not hydrogen and oxygen. We're going to save those for last. Once we have all the other elements balanced, then we're next going to balance the oxygens. We're going to balance the oxygens by adding water opposite to where the oxygen that needs to be balanced is. Sometimes there will be an oxygen on both the left and the right side of the arrow, both in the reactant and product side. So you're going to have to do a little bit of math in your head to figure out which side that water's going to go. So for example, if I had 4 oxygens on the reactant side on the left, and I only had 2 oxygens, or no, let's just say this. Let's say I had 3 oxygens on the reactant side on the left, and I only had 2 on the right, in the product side. If I add a water to the right product side, then that gives me a total of 3 oxygens. So now I'm balanced, okay? So sometimes it's very obvious where the water goes, opposite the oxygen. Sometimes you're going to have to do a little bit of thinking to discern if I have oxygens on both left and right side of the arrow, which side do I put the water on? Okay, once I got the water in there to balance the oxygens, then I need to put a hydrogen ion opposite of where the water is and throw a coefficient in front of that to balance those hydrogens. So we do this, remember, because these are already in aqueous solutions. So it's not like we're magically just throwing water in there somewhere. These are already aqueous solutions. So because they're already aqueous, that means hydrogen is already there. Now, the only added step for these done in basic solutions is we're going to have to throw a hydroxide in there, and I'll show you that when we get to that example. But the hydroxide, because it's a basic solution, is going to neutralize now those hydrogen ions. Okay? Now, once we balance the charge by adjusting the electrons and balance the electrons by using multipliers if necessary, then we combine the two reactions, and we eliminate anything that's the same on the left and the right of the arrow to cancel it out. And then, of course, we check. So if we look at this example here, this is just a very simplistic look at balancing half reactions. So the first thing we're going to do is we're going to assign oxidation numbers to each thing. Aluminum is in its free state, so its oxidation number is 0. And in the product side, it goes to +3. So that is a loss of 3 electrons. It is a loss, therefore is oxidized. The copper starts at 2+ and goes back to its solid state, which is its free state. So it goes from 2+ to 0, which means that it is reduced by 2 electrons. So we can separate out these half reactions now that we know what we're dealing with. And remember, on the oxidation side, if you want to put the electrons in the very first step, that's fine. That's generally what I do also. If you want to wait till you get to the part of balancing the electrons, that's okay too. So in this case, if you did it to begin with, the electrons would go on the product side. It would be Al3 plus 3 electrons. And on the reduction side, it would go on the reactant side. We would have Cu2 plus aqueous plus 2 electrons. Now, the first thing we're going to do is balance everything except the hydrogen and oxygen. But as you can see from here, they're already balanced. 1 and 1, 1 and 1. So they're balanced in and of their own right. We don't have to do anything with them. The charges don't account for coefficients to balance. It just tells you what their ions are. So we have 1 aluminum, 1 aluminum, 1 copper, 1 copper, 1 and done. It is balanced. So now we have to deal with any hydrogens and oxygens that are present. In this case, we don't have any, so we can skip the water step. There are no oxygens to balance. There are no hydrogens to balance. Had they been present, we would have added water to the opposite side of the oxygen, and then added hydrogen ion to the opposite side of the water. Because there is no oxygen to balance in either half reaction, we can go on to step 4. So that means looking at the electrons. Aluminum lost 3, copper gained 2. That is not an equal gain and loss of electrons. So we will have to use a multiplier here in order to make the gain and loss of electrons equal. What that means is the first equation I'm going to have to multiply by 2, and the second one I'm going to have to multiply by 3. That will give me a total of 6 electrons gained and 6 electrons lost. But if I do it to the electrons, I got to do it to everything else. So I get 2 aluminum 3 plus 6 electrons, 6 electrons, plus 3 copper, 2 pluses, yields 3 copper solids. Once I combine them together, the electrons cancel out. They are opposite the arrow, so they cancel out. And my net balanced chemical equation is as written. It's based on balancing the electrons, not randomly throwing coefficients in front of these. Now, to make this very clear, why balancing this way is much more effective and accurate than just our regular ordinary way of balancing. If you look here, there's 2 aluminums, 3 coppers. If we go back to the original, up here, 1, 1, 1, 1. If we had just left that as is, it's not technically balanced by way of electrons gained and lost. That's why we use this half reaction method. So now all you do is you just verify that, check your work, make sure everything is balanced. I recommend practicing this one. Okay, now we're going to talk about balancing in basic solutions. The only difference here is we have one extra step if it's basic solution than we would if it were acidic or neutral solution and there were oxygens involved. So we're going to do the same thing. We're going to assign the oxidation numbers. I takes on the oxidation number, I minus takes on the oxidation number equal to its charge, -1. And in its standard state, I2, which is its free state, it takes an oxidation number of 0. So it's going from -1 to 0, which means it is a loss of electrons. It is oxidized. We can do the math. We did this, I wrote this on the board today in class. If you were not in class, then get the notes from somebody who was. I wrote it on the board. I did not write it in the video recording integrity. But we could mathematically figure out that this manganese is +7 and this one is +4. This one we did not do on the board, but the process for calculating it is the same. So Manganese is +4 here. We go from +7 to +4. That's reducing the charge or reducing the oxidation state. So it is a gain of negativeness. Therefore, it is reduced. Now that we know that, we can write each half reaction separately. And I know your book and all these other places like to do them on top of each other. I like to write oxidation on the left, reduction on the right, so I can go kind of down a list so they don't get jumbled. Now we're going to balance all the individual elements that are not hydrogen and oxygen. Okay, so if we start with the first one, I have 1 oxygen here, 2 oxygens. I got 1 iodine here, 2 iodines here. So I use that coefficient 2 in front of it to make the number of iodines equal. Here, the manganese, they're 1 to 1, so I'm good to go. Now I'm going to deal with balancing any oxygens that are present. The first half reaction, there are no oxygens that I have to deal with, so I can just leave that as is until I get to the balancing of the electron steps. The second half reaction does, in fact, have oxygens. And this is one of those examples where I said you might see it come about where you have 4 oxygens on the left and 2 oxygens on the right, or oxygens basically on both sides. So how do we discern where to put the water? Well, if I said to myself, I'm just going to throw a 2 in front of this manganese right here. If I throw a 2 in front of that manganese, yes, that'll get me 4 oxygens, but then it's going to mess up my balanced manganeses. So this is the side that has less oxygens, so this is the side I need to add the water to, because I can easily throw 2 in front of the water and get 1, 2, 3, 4 oxygens, 1, 2, 3, 4 oxygens, bam, my oxygens are now balanced. But now I have to balance the hydrogens. Again, the first half reaction had no hydrogens, so I can leave it as is until I get to the electron step. The second one does have hydrogens from the water, so that means I have to put 4 hydrogens opposite the water. There's 4 hydrogens from the water, so I put 4H plus opposite the water. So now my hydrogens are balanced. And again, I'm not making this up out of thin air. It's already in an aqueous solution, so the water is already present. Now because it's in a basic solution, I have to deal with the hydrogen ions I just added. They have to neutralize. Iodine, that's first half reaction step. Again, don't have to deal with it, can leave it as is. But because we're in a basic solution, there is hydroxides present. Base hydroxides, base hydroxides. So I need to add as many hydroxides as I did hydrogen ions so water can form and it'll neutralize the hydrogens. And then if I add the hydroxide to the one side, I gotta add it to the other. And that keeps this basic. Okay, so some of these hydroxides are going to neutralize the hydrogen ions, and some of them are going to stay in solution because it's a basic solution. When we did the previous example, had there been hydrogens, or like the one we did today in class, that would keep it in acidic solution because there would be excess hydrogen ions present, more hydrogen ions than there are waters. Okay, so the hydroxide, because it's in a basic solution, allows this hydrogen ion to be neutralized. And then I'm adding the hydroxide to the other side to make it balanced and also to keep it basic. And remember, we're talking about a basic solution. So that hydroxide is already present. So now I have to deal with the electrons. The first half reaction was oxidized, so the electrons go on the product side. The second half was reduced, so the electrons go on the reactant side. Because it is not an equal amount of gain or loss of electrons, now we have to use a multiplier. So I'm going to multiply the first oxidation half reaction by 3 and the second reduction half reaction by 2. That will give me a total of 6 electrons gained and lost. Once I've done that, I can combine them. And what you will notice, this is also what makes it a little bit different. Yes, the electrons cancel out, but now because this is a basic solution and the base neutralized some of the hydrogen ions, which formed water, now we have waters on both the left and the right side of the reaction. So these all go away, and there's a leftover of 4 here. Remember, it's anything other side of the arrow and opposite other side of the arrow. Okay, so these electrons are opposite. These are these waters are other side. So the 4 waters cancel out and go away. 4 waters cancel out here. So my net is 6 iodines plus 4 waters, that's what's left over, plus 2 MnO4 minuses yields 3 I2s, 2 MnO2s, that water went away, and 8 hydroxides. Now you just have to check that everything is there and present, and that everything is good to go. You have everything balanced. You have the right number of stuff on the left and the right side of the arrow. I highly recommend practicing this one as well.